All right, greetings, everybody. My name is Peter Dyke. I'm the Executive Director of the Alliance for PE Pipe, and I am delighted today to be with you and share with you what we've got going here today in the 101. This is the deck that we give most of all throughout North America every year. We give it a lot, and we're just delighted we got so many people on the call today, so welcome. The Alliance is a not-for-profit trade organization. We're very thankful for all these companies that fund our operation. Without them, we really wouldn't be very active. So please support those that support education. So we're also excited. We haven't shown this one in a while. We're very excited to talk about the Peru project. Alan, could you give us a quick minute on what we're doing in Peru? And this year, last year we talked about it, but didn't get to go. And now this year, you and I are headed down there.
Absolutely, Pete. I'm glad that you asked. So we've used our microphone, and everybody out there is helping contribute to this clean water project in Peru as part of the Engineers Without Borders program as it goes through. And we are providing clean water, all HDPE lines to bring that clean water from the well that they're digging all the way down through to the village with the different taps to make sure that these folks, indigenous tribe in Peru here, doesn't have to now walk and take all the haul the water themselves. So if you just want to screenshot this or use your phone and take a picture right now, you're more than welcome to donate to this project. The Alliance has donated to the project. Some of the members of the Alliance have donated all the pipe and the materials. We're going to go down and teach these people how to maintain and fuse their own pipe as well. Another charity I'm involved with called Jam It for Water has donated to it. There's certain steps that has to happen to be able to get to the piping, and we're close. We're right there. So everybody's assistance with this project is so appreciated, and certainly moving things forward for water for people. Thank you very much.
Hey, Alan, I'm excited about it. I don't know that I'm excited about climbing up the mountain with you, but I am excited to serve this tribal, this native indigenous group of people.
We're going to do it, Pete. I know.
So we have 32,000 people that follow us on social media. Join us. We're posting every single day. So right this week, we're down in Houston at Texas Water, which is a fantastic show. We're going to be up in Anchorage and Juneau here in a couple weeks. We're going to be in Washington, D.C. Alan and the engineers are all going to NoDig in Denver this year. And then, of course, we'll be in Alberta as well. So if you're in any of those areas, please come see us at a road show. Alan, come on one more time. Introduce yourself, please, and tell us a little bit about the engineers package and how people can get involved with us if they have a project that they might need some help with.
I'm glad you asked, Pete. So we get emails all the time about different projects that are going on. We love to talk about high-density polyethylene, and we're here for you to be able to schedule a seminar with any of our experts for your specific question that you have. It's kind of like lunch and learn, but all on Zoom as we see it there. Pete, you moved away from the slideshow. And then we essentially will set that up to look at your particular project. We'll review your project or look at your specs and help write your specs or edit the specs that you have to be able to include the best possible avenue for high-density polyethylene representative. D. Landy at pepipe.org is our fellow that handles all of this for us to be able to go through and make sure that you're connected with the appropriate experts to be able to answer your problem. And we get involved all the time to be able to help advance your project. So you can also go on pepipe.org in order to be able to look at our engineers package, which would be the next slide in that association there. And essentially that engineers package has an insider's guide to vocab, has different terms and conditions, standard details, case studies. Nobody wants to be the first one to do something, but I can tell you, you're not. There's lots of people that have done that before, and we have those case studies to be able to help you understand how HDPE works in your specific scenario. So all these are free resources on pepipe.org, or if you want that seminar to talk about your particular project, email us at info@pepipe.org or dlandy@pepipe.org.
Thank you
All
for
right.
that, Alan. One other procedural question in audience. Sorry, these guys hate it when I run the deck, but I just tried to click on sound. I don't know that I have sound, Alan. So if you can help me with that, I'd
I will
appreciate
take a look. Yeah, absolutely. Keep
it.
going.
So we got a lot of people to say thank you today for helping us put this deck together. So without calling them out individually, here they are on the screen. We are thankful for the many people that have come before us and have educated us. So thank you, everybody who's participated. We also have a lot of technical references from today, as well as publications. So today we have myself as the lead speaker. We've got Ian Detloff. Hey, Ian, come on and introduce yourself, would you please?
Yes, Peter, thank you for the introduction. My name is Ian Detloff. I am currently serving as the project manager for the Alliance, and what I do with that is just help with a lot of our event logistics, a lot of our marketing, a lot of our social media posts, and as well as some administrative stuff on the back end. And today I'm going to be focusing on a couple of projects where HDP is saving the day.
Absolutely. Yes, you are. We're thankful for you. And everybody, this is Ian's maiden voyage presenting in the webinar program. And a familiar face is Richard Colassa. Richard, come on and say hello.
Hi, good afternoon, everybody. Thank you, Peter, for having me today again. I believe the 101, when we look back almost 12 years now, was the starting point of everything that's going on. It's developed and we've grown a lot from the information that and the feedback we've got from the audiences to build a really nice program to really get a nice basic understanding of polyethylene. And it's a really great starting point because it'll give you hopefully a lot of references and a lot of avenues to look at if you're just learning about polyethylene today.
Yeah, Richard, you've been a great sidekick over the years. And then Stephen Boros, Dan Landy, and John Stevens, thank you guys for being on the bench. Stephen, tell us about the bench.
Yeah, so we got a great bench back here for you guys today. So we are on the Q&A function. We'll pop in from time to time and add a little color to the group and discussion, or maybe some points. We might come on and answer some questions live that were asked. So be sure and use the Q&A function, and we'll get them answered the best we can.
Good. Thank you, Stephen. All right. So here's how you get a hold of us. Just take a screenshot of that if you want to send Stephen an email. Stephen is a very experienced engineer that's taught me an awful lot over the years, as has Richard Colassa. So, Ian, I'm going to turn this over to you now since I've thoroughly screwed it up. Take it over and let's talk about how polyethylene saves the day.
Yes, thank you, Peter, for the intro. Essentially, today we're going to be focusing on a couple different projects and then focusing on what a best practice is and how it is already being used in major corporations around the U.S. So here, as you can see on your screen, we have the definition of a best practice. It's a procedure that has been shown by research and experience to produce optimal results. Awesome. And then, as I just referenced previously, we have Google, Apple, and Tesla who are active users of a high-density polyethylene in many different scenarios when they're building their new plants. Most recently, out in Austin, Texas, Tesla built their plant, and to set that up, they had to create an 18-inch water line that they drew out from the city to the plant. All right, here's our first case of the De Helveman Brewing Company that is located in Bruges, Belgium, a very big tourist area for the Belgium itself. Here, the brewery's been around for years and years and years, but as we've progressed through time, the tourism and just the density of the city has affected the process of brewing. So essentially, they had to create a new plant. As Peter has up on the screen, you can see the image on the bottom right is where the brewery is located, and they had to create a main all the way to the bottling plant because they had trucks running through the city and it was disrupting the tourism. So essentially there you can see the pipe being implemented into the tight and confined streets of Bruges, Belgium, and it allowed them to send about 12,000 bottles per hour via the beer main.
Yeah, pretty excited to have a beer main reported about made out of polyethylene in the Wall Street Journal.
And two, to that point, it was a crowd-funded operation, which is pretty unique. All right, our next one comes from Cape Town, Africa. It was reported in the the New York Times down there in the bottom picture. You can see in the airport, they were saying, do not flush the toilet. It got to that bad of an extent. The lake up in the upper right is basically showing us how low they got with the ready water available. In the bottom left, we had the military handing out water bottles because we were running out of water. And one of the ways they combated it was by creating 7 desalination plants right on the beaches in Cape Town. On the right, you can see an image of the Hdpe strung out, and it shows the ductility and the ability to bend it around, but also you can see the concrete anchors, which are in place because, as you can see, the high-density polyethylene is exposed to the air, so we gotta support it and make sure it's not bending. All right, the next big one, probably most notable for everyone on the call, was a Thai cave rescue. They had a little bit of break between 2 soccer games, and the coach decided to take them into the cave, and little did they know that it was going to be filled up and trapped for a number of days. So here, some people from Xylem sent over some of their engineers. After a couple of days, they were able to meet with the head general, and then they were able to basically string up multiple different high-density polyethylene lines, and excuse me, also some medium density, which is our yellow pipe laid out through the cave as well. But essentially, they were using those pipes to dewater the cave as well as bring oxygen to the trap players. Next one. All right. As Peter always likes to say, back in the day, sinkhole used to be associated with a limestone formation. And now, too often, we're finding it being a cause of a water main break. So this is Peter was able to go up to Macomb County, Michigan, and essentially they had a major failure that took down 3 homes where ended up being condemned. But in turn, they were able to create 2 dual 36-inch pipes as a bypass, and they connected it in that main picture with flanges as well as butt fusion. There we go. I kind of alluded to that, but it was about a 4,000 linear foot failure. So we were able to get those 2 dual 36-inch pipes up. And when Peter was out there, he was meeting with the county commissioner, and she simply said that this PE bypass was an engineering marvel. All right, here's 2 cool examples. The one on the right I'll get to in a second. But Alan and Peter had the pleasure of speaking with a couple of guys back in Indiana a couple years ago. And they basically showed them this image on the left. And the reason that the pipe is strung up in the river is because the locale didn't allow them to use the right of way in the street lanes. So they found out a way where they could just string the 4 8-inch pipes through the river. And the reason they could do that is because it's a fused monolithic system. There was no leakage there. The video Peter's beginning to play is actually we found out when we were down in Baton Rouge earlier this year, and they had a 72-inch gravity sewer main failure. So in turn, they had to create 4 different or numerous pipes to combat that. And the old system was moving 72 million gallons a day of sewage. So it was an emergency project. All right, and finally, a different alternative example to Hdpe and pipe material. There are boats. This guy, Bruno Tideman, is creating Hdpe boats. It not only floats, but it also is not going to leak as well. But you could watch that movie on Netflix. It is called 6 Underground.
All right, Ian, thank you very much. Good job. Let's hear it for Ian, even though we can't let him know because we can't hear you guys. Now we're moving on. Thank you, Ian. Into Hdpe markets. So why do we care about the markets? Well, because polyethylene plays in all 9 of these markets. We dominate 5 of them, yet our primary competitors, PVC and ductile. Ductile is really only in 2 and PVC is in 3 because the other markets have rejected them for a variety of reasons. I love this image on the right because it shows that's a piece of pipe from here. That's polyethylene strung out into the James River in coastal Virginia. This is a fantastic Garney job for the Hampton Roads Sanitation District that broke a lot of barriers for diameter and depth of pull. So the landfill market, imagine PVC doing what polyethylene does in the landfill market. Polyethylene is used 3 different ways. So it's the membrane that protects our groundwater. It's also leachate collection as well as methane recovery, all the same pipe or polyethylene. So here we have headers picking up the methane. We can drill polyethylene so it can take those gases and send them up to the headers, and that methane can then be used to power millions of homes every year. So polyethylene dominates the landfill market. Just think about the ground is always moving. Polyethylene is perfect for that. We also dominate the geothermal market, also not a huge market for polyethylene in general, but basically we're running lines horizontal as well as vertical. Here's a great detail on the left-hand side, and a good demonstration on the right of polyethylene lined up together, taking advantage of the Earth's energy for ground source heat exchange. The coolest version of this geothermal idea comes out of Enwave, which is a municipal entity in Toronto, where they run 63-inch lines, 4 of them, in fact, out into Lake Ontario to take advantage of the temperature down low in the depths. So for cooling in the summer and heating in the winter. Richard, could you come on and tell us why all these concrete collars are on there?
Yes, Peter. So of course, polyethylene has a buoyancy less than 1. So that means it floats in water, water having a buoyancy or a specific gravity of 1. And the collars are used to, and spaced and sized and weighted. Once you determine the length and the size of that pipe and filled with air, you'll understand the buoyancy. So then you can add weights to put it down to depth. So in order to sink that pipe and get down to the depths for that colder water, then you need to be able to sink that pipe down. So typically the way it's done, especially in marine applications, is we will determine the buoyancy and the collar weights just to take that weight down once it's filled with water. So then if you empty it out, then you can raise that pipe back up if you had to do any maintenance in the long-term future as well. So it's buoyancy related, and that's why those collars exist.
Yeah, I always struggle, Richard. I don't know whether to call this marine or geothermal, but I look at it as a market. Thank you for that. And we've got Holland, Michigan, Richard, where they're using waste energy from their electric plant to heat the sidewalks. They're on the right. So we've got the outbound water in red and then the inbound water in the blue. Very cool. And in the irrigation market, I break this into 2 categories, golf course and agricultural. Golf course used to be dominated by PVC. And now 90% of installations, both renovation and new and golf, are polyethylene. So PVC's taken a bath in that market. Hats off to the many polyethylene distributors there. Stephen, go ahead.
Yeah, Peter, there's a really good reason for that. When you think about it, golf course irrigation is a really rigorous process. I mean, you got pumps and sprinklers and valves turning on and off all the time. Rarely is there a lot of air release valves or controlled valves in any way. So you got to remember that whatever material is used in that application has to be extremely tough. And what they found over the years is that they don't have to replace the irrigation systems with polyethylene because they don't fail with cyclic fatigue.
Yeah, well said. The cyclic fatigue thing is often misunderstood and not often realized enough. But to your point also, Stephen, most golf course superintendents don't put the polyethylene below the frost line because they don't have to worry about it, because the polyethylene just move with the earth.
Yeah, that's right. And it's interesting. One more point real quick. I don't want to get hung up on this, but the city of Tishomingo, Oklahoma, the city manager there, when they had to redo their water line for a new well they were drilling to bring water into the town, his previous experience was with golf courses. He used polyethylene pipe on golf courses, and it worked so well, he wanted only to use polyethylene on this system for his city as well.
So thank you, Stephen. So on agricultural, Richard, would you mind coming on? We've got a 2-meter diameter almond farm being irrigated with polyethylene there on the right using McElroy's Talon machine. And then Richard, we've got some WL pipe here on the right. I don't see any joints.
Yeah, that's just because of its ductility. I mean,
fittings. I don't see any fittings. Sorry.
Or you don't see any fittings. Yeah, and so it has a minimum bend radius, and we understand that bend radius maximum that you can bend this pipe. So if you're within that acceptable bend radius, then you're allowed to bend that pipe. And in this situation where they're taking that corner around whatever roadway or whatever it is. You don't have to take the time. You just bend it around and then lock it in and probably bury it at the end of the day, and
Yeah,
it'll be
those-
just fine.
Those are
If you-
twin 36-inch limes. I
Yep,
mean, that's just
you bet.
fantastic.
Yep.
So, hats off to you guys and your team. So here's a 2.25 meter in the lower left-hand corner. When we get above 2 meters in diameter, we see blue machines. So these are usually rented by Agru. Agru is making up to 11-foot diameter pipe now down in South Carolina. They're shipping it all over the world. It's really very exciting. So this is the condition of the existing canal. Loses more than half of its water. So you get the idea. So that's on the agricultural irrigation side. That was for an irrigation district in Arizona, where in some cases they just laid it in the decayed open trench. In other cases, they just dug a trench next to it. But we're working on these every day in our industry. Pretty exciting. So we're, instead of losing 40% of their water or 50%, they're not losing any of it, basically, because they don't have any leaks, and you get a much lower evaporation rate. There's polyethylene on the side of a mine. This is a market we don't dominate. We share it with steel. But Stephen, could you come on and explain, when you're running a slurry in a pipeline, you're worried about damaging that pipeline because those rocks aren't always in suspension. So what do you do with the polyethylene, and why do they like it so much?
Yeah, that's a good point. So polyethylene is used much more than steel in these applications. Again, because of its toughness, even if the particles fall out of suspension, which they do a lot of times, and it can cause significant abrasion. They found that polyethylene pipe lasts from 4 to 10 times longer than steel, depending on the type of aggregate and how abrasive it is in these applications, simply because the particles tend to bounce off of it rather than score it and gouge it and erode it over time. So dredging, mining, and things like that, they'll go to polyethylene 9 out of 10 times.
Here's a basic fact, Stephen. What's our rule for gouging and abrading polyethylene?
Yeah, once again, so the rule of thumb is that as long as a scratch or gouge is less than 10% of the wall thickness, the entire wall thickness, then the gouge or scratch is considered benign and it doesn't need to be cut out. If it is deeper than that, then it's very easy to cut out that section, fuse the pieces back together, and you got a monolithic piece of pipe again. So 10% is the rule of thumb. Any less than that, leave it. It's no problem.
Good. Thank you. Now, moving on to the industrial side, this is a market we share with pretty much every pipe type except maybe clay and probably not concrete too much. Although in the nuclear industry, polyethylene is, in order to keep nuclear power plants running, polyethylene is replacing and lining the concrete, which, all these plants are more than 50 years old. So that concrete is at the end of its life. So polyethylene is now permitted by the Nuclear Regulatory Commission. Richard, could you tell us a little bit about why the dredging industry loves HDPE pipe?
Yeah, the dredging portion of it, I mean, it's flexible and it's movable. So you can actually, because of its viscoelastic behavior, you can move it around. And when you're dredging, you're typically moving the pipe around. So it's again, as Stephen alluded to, its toughness. You're allowed to move it. And so if you're dredging and moving that material around or having to move that pipe around into different locations, it's not an issue.
Yeah, you're
You
moving the
still have to
barge.
use best practices. I'm sorry?
Yeah, you're moving the barge. The pipe is laying in the water. The pipe is sunk in the water. The pipe is on the barge. The pipe is connected to the shore. Some of that dredge material is wasted or is sent onto other barges or onto shore, right? And
That's
your
right.
pipe can go in every direction.
That's correct. And it's like I said, that toughness and its ability to withstand those movements. And like we had a webinar or a podcast not too long ago with people installing it in Alaska, and it actually froze to the surface of the ice, and that ice was moving, yet they managed to take it off. And there was nothing wrong with that pipe. It moved with that ice, which was very fortunate. Any other product for any kind of dredging or water movement, it would have broken. They would have had failures.
Thank you, Richard. So now we're moving still in the industrial market to district energy, which is a huge growth area for us. All these colleges and universities are using polyethylene in a big way. Texas A&M has been a leader in this, and we got Ruben Bernal on film.
For years, we've always did it with mechanical joints, steel, direct burial, carbon steel pipe, and just like anything else, it all decays in the water, in the ground. And we had multiple leaks, and we looked for an alternative way to not use metallic pipe and first. We are the first, and a bunch of universities are asking questions to us too. We've been having good luck with this pipe. We hadn't had any issues, and it's different, but it's in the long run, the benefits are great. A normal day, we could see 50, 40 gallons a day. I mean, a minute, because we had leaks here, leaks there. And we repaired all the bad spots, and now we're down to single digit numbers. You don't see that often. So we're averaging between 3 to 8 gallons a day on main campus. That's for years, we've always did.
That's incredible. Ruben is an advocate. They've been using the product for over 20 years. Above ground, we did a webinar on this last week, or on ground, at grade, however you want to describe it. Polyethylene does get affected by the thermal effects of the sunlight, and it needs to be restrained in this application. Go ahead, Richard.
Yeah, and that's really important to understand. I know a lot of the calculators that we have online for your use calculate an unrestrained movement for temperature change. Just remember that. So those clamps are between those certain lengths. That's going to restrict that movement. So then you can divide that movement or the expansion or contraction on that pipe between those clamps, and to a point where you can eliminate it. You can, by the looks of that suspended pipe on the left side there, I mean, you're probably locking that right in. But one key thing to always remember, and it's in the plastics pipe handbook, the PE handbook, is when you use a metal clamp, please use a rubber gasket associated against the pipe, because that movement and stress is then cushioned against the steel, because the steel does have the tendency to wear the plastic out over time. So it could create an unanticipated gouge. So just make sure you follow those rules and use the best practices for installing those clamps.
So, once we get started doing Alliance webinars, once we get through those first 8 minutes, we get going pretty quick. And this is intended to be a survey course. So we could go deeper on many of these issues. Richard and I hosted on the podcast last month a fantastic engineer by the name of Adrian Hanan. And Adrian gave us these images, and I was just dying to put them in here. So this is the first time we've shown these publicly with his permission. But there he is putting on a concrete anchor on polyethylene. Each one takes hours to put on properly to avoid the problem Richard talks about. But we're talking about outfalls and intakes. And Adrian tends to work in extreme environments. So think the Arctic. Here's an image of, he's installing one. These are steel. Actually, Richard, these might even be concrete. But take a look at this.
Yeah, they're they're concrete and steel reinforced concrete, but that's what he's using as his blocks and the way he's got it anchored. But he needs the mobility. As you can see, he couldn't. This line came out, and this is the one that was stuck to the ice, and then they needed to raise it up so they could have access to it. And then, but the seas were so rough they couldn't get out there. But it's going through that 2 or 3 days, he said. I can't remember the time factor, but they couldn't bring the boats on the water for 2 or 3 days. So it's sitting there, and there's a lot of stress on that endpoint. And so just to reiterate what Stephen said, that doesn't fail by fatigue. There's a lot of fatigue going on there, and to have that pipe perform after the fact is pretty remarkable.
Yeah, he's working on some fantastic projects. I encourage you to listen to the podcast. You'll find it on our website. Okay, natural gas market. So back in the 60s, when we commercialized polyethylene, this is one of the markets we went after. We now own this market. So any natural gas distribution pipe that's being replaced today or as a new install is all polyethylene. The industry has tried many other pipe types, mostly bell and spigot, and they've given up because they leak, particularly near the end of their lives. So we own this market. Steel owns transmission. We own distribution. Ian, come on and tell us a little bit about this squeeze-off tool and how and why you can squeeze Hdpe pipe.
That is a footage squeeze-off tool, and that looks like it might be, they go in ranges up to 24 inches. And in this picture, it's for a gas line. So if you had any sort of break or you had to work on it, you could squeeze that all the way down. So there would be no open area. You'd have no flow anymore with that. As they get bigger, they become more hydraulic. We do carry around, I believe, up to a 2-inch squeeze off with us on our road shows, and that's a manual option there. And you're able to squeeze off in the same location, but after that, we would suggest moving over at least 2 diameters of the pipe over.
Great. Thank you, Ian. And here we are installing a 6-inch medium density polyethylene, a 2-inch telecommunications conduit, tracer wire, and caution tape, all at the same time using a plowing tool. So we also went after the oil and gas market in the 60s and 70s, and we dominate here as well. So think about horizontal pipes. The steel pipes are vertical, so those are high pressure, high temperature. We don't do well in those circumstances. So that is carbon steel. So here's polyethylene running crude oil from the drilling site, the drilling rig, to the intermediate storage tanks. Richard, come on and tell us a little bit about our sustainable proposition. Here we've got natural gas being vented at the wellhead. Where does our resin come from?
Yeah, that's a good point, Peter. In the past, or in the early 1900s, or when polyethylene was invented, before it was invented, when we separate these gases and we crack them into their various components of methane or propane or whatever it may be, gasoline, we get ethylene. And ethylene is a byproduct, and so that ethylene would literally be flared off. And of course, with all the initiatives with having a greener earth and reducing carbon footprint, it was discovered that the methane or the ethylene could be used as a building block for polyethylene. And that was Ziegler-Natta that developed a catalyst to open up that double bond between the 2 carbons and then create these chains of polymer. So then, of course, there's lots of different polymers you can make from that. So it's how you make it, and our pipe grade is made specifically for pipe. So those flares are becoming less and less. You need them for operations as a safety factor in case you have some kind of backup and pressure relief, so you can vent off and burn. But for the most part now, that's been drastically reduced because we take that gas, we crack it into its ethylene components and purify it and make the plastic components out of it.
Awesome. Thank you, Richard. So counting down, we got 2 left, municipal. So here's a market that's primarily dominated by PVC. 2 generations ago, it was dominated by ductile iron. But PVC is a good product. It's better than ductile iron because it doesn't tuberculate, but it is brittle at temperature, and it is a bell and spigot system. And when the ground moves, it can crack. We don't have that problem. But I break out the municipal market into 5 areas, and we have a different competitor in each one. And we have different percentages of share in each one of these 5 markets. It's kind of exciting to know. I mean, we're up and to the right constantly in each of these markets. And the big market today for us, Stephen, is that large diameter transmission market. Tell us a little bit about that and what polyethylene's doing.
Yeah, I mean, I think these are good segments of the water market. People have to understand when you say water, it doesn't just mean one thing. But transmission is an area where polyethylene pipes really grown in the last, I'd say, 5 to 8 years. All these transmission lines usually bring you raw water or treated water, could be potable water as well, into cities, municipalities, and things. They're old. I mean, they're 40, 50, 60, 80 years old, and they're failing and they're leaking, and water is becoming more and more precious, especially in these areas in West Texas and Oklahoma and out west where we see water leakage rates very, very high. So polyethylene is being used to replace these systems very quickly. It can be installed faster and cheaper and give you a fully leak-free monolithic piping system in these transmission lines. It can be operated at higher flow velocities if you need to, because polyethylene can handle the additional surges at these high flow velocities that other materials don't without having to derate the maximum operating pressure rating of the product. So it's quickly being found, especially in these rural applications where the cost of the project is predominantly in the piping material and the installation cost. Polyethylene will save a considerable amount of money in those situations and provide a 100-year plus design system.
Yeah, it's pretty exciting. Although, Stephen, everybody says their pipe's going to last 100 years.
They do. So there's differences. So you can claim a pipe can last 100 years. Cast iron says our pipe has a 100-year service life because we have a piece of pipe that has lasted 100 years. But that's service life is different than design life. I like to define it two different ways. So when you take all the aspects and design of the system into place and you design for those criteria and those limitations of the individual product, and you say these design mechanisms will not cause failure in 100 years, then you have a 100-year design. If you just say, oh, it has a 100-year service life, I mean, you never know the service life till you reach the end of it. I mean, you might design for 50 years and it could last for 100 years. That doesn't mean you designed for a service life of 100 years. It just happened to work out that way in the way it was being operated. So there's a big difference in design life and service life and what you're really defining there.
Thank you for that explanation. Stephen, there has been some market confusion over the years because our early generation, first and second generation polyethylenes, we said had a 50-year design life. And that pipe lasted about 50 years. Now we're saying it's 100 years, okay? Yeah. And then we had this study come out 3 years ago now, Stephen, from the UK WIR, where it said that the first and second generation polys that they exhumed that were in water service, that had chlorine in it, was going to last 160 years. Tell us about that.
Yeah. So again, I think you're looking at the difference between design life and service life. It depends how the system's being operated. What they found is that in these systems where in the UK, because they've been using it a lot longer for all these water applications than we have, they found that once polyethylene was used and designed in those systems, they lasted. They may have only considered they were going to last 50 years because, at the time we were still, 50 years ago, we were trying to figure out what were the predominant failure mechanisms. Now we know what those are. The fourth generation of materials today are even better against those types of failures. And so even though they lasted 50 years more or 100 years previously, today's materials are 10 to 100 times better than that.
Yeah, well said. Thank you for that. I'd like to talk about, Stephen, that image in the lower left, because a lot of utilities, when they first start using polyethylene, they say yes to the main, but they still want to go mechanical on the connection.
Yeah, it's an old habit. It's just easier. You typically have different people installing the service line sometimes than you do the main. So it's just have maybe their comfort level with it. But best practice and best recommendation for polyethylene is to use a fuse saddle, such as you see in the middle lower picture there. Electrofuse saddle means it won't come off. It's monolithic system, and you can connect right to it. You can see that the picture you pointed out here on the left, you can see all those services right in direct line, very close to each other. With other types of materials, you're not allowed to put, first of all, you're not allowed to put them all on the same line. You have to rotate them around the pipe. And secondly, you can't put them that close together. With polyethylene, You can put as many as you like right next to each other. The cracks aren't going to grow from one hole to the next when you cut out that service connection, and you're not going to have to worry about it. Plus, with polyethylene, since you can squeeze it, you don't really need a corp stop any longer either. So you're saving money with that.
Yeah, I love this one because
Yeah.
we've got a polyethylene main here. We have a mechanical corp saddle to a brass corporation, to a branch, and it's a polyethylene service.
Yeah, they've taken a lot of additional costs and difficulty and potential leak points when they didn't need to. Just
We should
because
do a whole webinar just on services. I think we will. We'll do that next year. So conduit, 2 billion pounds a year. It's that orange and other colored stuff you see in the side of the road with an occasional drilling machine. This is a lower grade of polyethylene resin, but nevertheless, it's polyethylene. And look at what you can do with it. You can plow it in. So here on the lower right-hand corner, we've got 1, 2, 3, 4, 5 conduits going in with tracer wire and caution tape at the same time. We have bundles that get pulled in. So conduit is really a pretty wonderful use of HDPE pipe. So we've got 5 different markets that embrace polyethylene to where we own that market. 4 others that we play and we share. And PVC has settled in municipal, as has ductile. PVC is also in irrigation and industrial, as is ductile. So you can see that all these markets use polyethylene, but they all don't use PVC and ductile. Maybe there's a reason for that. I love this image on the right because it shows us an electric fusion self-tapping tee. I consider this to be the best practice in polyethylene connections because, as Richard said, it's just not going to leak once it's fused. So then we have a reducer from a 2-inch. So this is a 6x2, so 6-inch main, 2-inch outlet, reduced down to a single inch, and that electrofusion coupler then is connected to that 1-inch service connection where we then have our tracer wire. All right, now we're going to talk about a few numbers. Polyethylene has been around since 1959. It was commercialized in the mid-1960s, about the time PVC was. We lose 2.1 trillion gallons of water a year. One of our key selling propositions is once you fuse it correctly, we're not going to leak on you. So we like to talk about what other pipes leak. 240,000 water main breaks. This data is a good 15, 18 years old from AWWA. So water main breaks are a thing that utilities work with every day. Utilities that use polyethylene, water main breaks doesn't happen unless it's third-party damage. The average water loss for the US or Canadian utility, 14%. The VIG between what ASCE says we should be spending and are spending on our infrastructure on the water and wastewater side is 1.4 trillion US dollars. And last year we put in 19,000 miles of HDPE pipe in US water and sewer systems. So that's what about a 15% market share looks like. What is HDPE? It's that stuff that's in your garage. Those containers are all made out of polyethylene. Some of it's high density, most of it is. Our polyethylene is a very high quality resin specifically designed to be a pipe, not a container, but a pipe. Those containers are designed to die within a period of years. Us, we're designed to last well over 100 years. So if you hear the phrase PE, MDPE, 47, what does it mean? It all pretty much means the same thing to us. This is that high density polyethylene used as a water or wastewater pipe in the United States. Our key selling proposition is we don't leak. How do we get there? We do a fusion. We clean it, we shave it, we heat it, we fuse it. We stick it together using heat fusion. We get this double rollback bead. That joint is as strong, if not stronger, than the pipe itself. It's really stronger, but they only let us say we can say as strong. That double rollback bead is an indicator that you did the fusion correctly. It's also an indicator to an inspector and says, hey, if that bead doesn't look proper, perhaps we should cut it out and refuse. Prior to this fusion process, we do something called facing. We face those pipe ends, we get that oxidative layer off there, and we get those pipes so they're directly aligned with one another. That allows fusion to happen properly. And there are various things you can do to evaluate whether the fusion tech is doing his job correctly or her job. Clean it, shave it, heat it, fuse it. Now, that proper fusion process yields a bead. And here's that bead showing up on the inside of the pipe. So Richard, we've got a bead on the outside. We've got a bead on the inside. Where's our flow?
Yeah, well, the flow goes over top of the bead, of course. There's been lots of discussions from engineers about what that tuberculation effect is on that pipe, but polyethylene has a.
You mean cavitation?
Well, it could be cavitation as well. Yeah, sorry, cavitation. Thank you very much. Did I say tuberculation? I think I did. Anyways, but that bead, with the bead in that pipe, the Hazen-Williams factor still remains at 150. In larger diameter gravity flow systems, where sometimes you'll have a big sewer line of 54-inch diameter sewer line, those beads can get quite large. So depending on the grades, and anything less than 3% grade, we can remove those beads from the inside. But typically in a high flow situation, nothing will adhere or stick to the polyethylene, and it also doesn't promote any biological growth either. That flow will remain the same over time. So low flows in gravity systems with slow grade or light grades, you'll get some buildup behind those beads, but in the reality, in a pressure pipe system, you do not need to remove those beads at all.
Yeah, thank you for that. So during the heat soak, when we're preparing the pipe ends for fusion, we got to heat them up so they can fuse. So ASTM F2620 tells us we got to have a bead, and that bead size is an indicator of, are we ready to fuse or not? So we're on time here. Alan Ambler, how are we doing? And how are we getting any questions today?
Lots of questions, Pete. You're doing great. Everybody is too. Richard and Stephen, of course, are doing better than you, Pete. I'm sorry, but that's just part of the expert that we have there. Lots of good communication. Remember, everybody, there, the Q&A is perfect for your questions for us.
So here we have a bead trimmer on an 8-inch. This is a WL Plastics pipe that's got the gray inside, so it's easy to camera. But that bead trimmer goes inside. You turn it in the opposite direction for 360 degrees. And then you'll notice here that the cutter blade pops out, and then it goes to work and it starts removing that bead. So that's what we call a bead trimmer. So the record is 500 feet down into a pipeline. Somebody forgot to do their trimming and the owner made them do it. But typically it's going in about 54. It's a 54-foot long pole, and we're cutting that bead out shortly after the fusion process. All right, so what is your main concern about switching from PVC to polyethylene? Yeah, that's most of the questions we get these days are people switching from PVC to polyethylene. That's more normal than people going from ductile to polyethylene, but it's kind of interesting. 90% of your fusions are going to be butt fusion. That's that image on the right in the trench. Alan, go ahead and close that out. 10% are going to be electrofusion. So electrofusions are both couplers as well as saddles. So we have a saddle on the right, that's a corp saddle. So it's a corporation. It permits us to put our corporation into that electrofused saddle. And then on the left, we have a coupler. So then we're using a coupler to fuse two pipe ends together instead of butt fusion. Couplers are fantastic for in-ditch tie-ins. So we're taking a drill, connecting it to an open cut, or we're connecting two open cut pieces together. Fantastic method known as electrofusion. All right, as a reminder, this is a 75-minute webinar. We've got 20-some slides left. We're running on time, so please fire more questions at us. We do want you to understand what DR is. OD divided by min wall gets us our DR. It's nothing more than a ratio of the diameter and the wall thickness. It's not a standard here, DR11 for water. It's not a standard, but everybody uses DR11 for water. A couple of people in the industry get so mad at me when I tell people that, but it's the truth. Somebody says, what DR should I use in my water system? I'm running an 80 PSI system. Well, you really only need a DR17, but everybody uses DR11. It's just the way it is. People use DR17 for sewer, whether it's a force main or a gravity main. It's just kind of like where the industry has settled. Those are what the facts are. I like to share in facts. Stephen, could you tell us about the relationship of our working pressure to our two different surges, please?
Sure, Peter. So are we going to the next slide? Oh, you got surge on here. Okay, yeah. So with polyethylene, you get a working pressure rating based on the maximum design stress of the material, but you also get surge allowance on top of that. So with polyethylene, you get a recurring surge, which means it can happen up to 55 times a day for 100 years, and you can go 1.5 times above that maximum working pressure rating. So for instance, you see the DR11 here has a 200 PSI working pressure rating. As long as you don't have surges above 400 PSI for occasional surges, you're fine. Up to 350 PSI, 300 PSI for recurring surges. That means you can flow probably in the range of around 10 to 12 feet per second. And you would not surpass these surge allowances that polyethylene has built into it. Other materials, depending on the way their pressure class is defined, and every material is different. Every AWWA standard designs pressure class differently for ductile iron, PVC, and polyethylene. You will have to derate that product if you have surge going on in your system. Depending on the material, it's going to be different. So it's up to every design engineer to understand that and to derate their product if they do have those limitations. Polyethylene doesn't have that limitation. So whatever the working pressure rating is, you have all this surge capacity above that without having to derate.
Well said, Stephen. Thank you. Richard Colassa.
Yeah, just quickly, Stephen, on top of that, the pace calculator in PPI lets you do those comparisons between the metals and the different plastics. So then you can take into account with your particular let's say water system, you can look at that, your how it operates and what those surges are on a regular basis, and you can calculate life expectancy on those lines.
Yeah, that's a great tool, Richard. www.ppipace.com lets you do those direct comparisons of PVC, polyethylene, and ductile iron in your actual operating conditions and see what the comparisons are. Good point.
All right, Richard, you got 30 seconds. Tell us how we know that we don't suffer from fatigue. 30 seconds.
Simple. There's been studies out there where we put polyethylene with fittings, connections, electrofusion couplings, all different types of fusions process under dynamic testing applications, and tested them for over 10 million cycles, and we didn't get any failures. So it's pretty hard to, and they were pretty extreme conditions, elevated temperatures plus way beyond the occasional or the occasional surge events. So we didn't get any failures. The other thing is under normal operating conditions for even a municipality, we're not even coming close to the tensile limitations of that product or the hoop stress capabilities of that product. So it's not a real complicated thing, but a lot of work has been done to understand that fatigue. And it's just because, in one word, it's viscoelastic behavior. It actually absorbs that energy and disperses that energy, so it doesn't magnify it. And that's my 30 seconds.
Yeah, I thought it was 15 million cycles. I heard you say 10, so am I wrong?
I thought it was 10 million for all of the different components tested. There could have been samples that were extended longer on the parent pipe itself. That number I could look back and confirm for you. It's not a big, it's done with GTI. Yeah.
All right, thanks. We have 3 different sizing conventions: CTS, DIPS, and IPS. So DIPS is slightly larger than IPS. Why do we have 3? Well, CTS is for the small, under 4 inches. IPS is all 9 of those markets that I talked about earlier. They all use IPS. We use DIPS in water, half use DIPS, half use IPS. But if all those other markets are using it, that's why IPS is always available. And DIPS does become a little more cumbersome in some of the longer runs. So if you're doing a 2,500 foot DIPS job, 24 inches, you might not be able to pull that from stock. That might have to come directly from a manufacturer. So ask your favorite distributor, what do you have in stock and what do you recommend, IPS or DIPS? All right, moving on to section 4. We got about 20 minutes left, 15 minutes left. We're going to finish on time. What is the data logger? So the data logger is a machine. Think iPad connected to my McElroy Fusion machine that allows the stakeholders to monitor what's going on even when you're not there. So you fill out all this important stuff. We can teach you how to read this data logger report, but really what it's doing is it's measuring pressure in the cylinder over a given period of time. And a beautiful data logger report, which is what we're seeing right here in front of us right now, tells us that that fusion tech is paying attention to those details so that we know that that pipe is going in the ground the way we want it to. This long run here from 220 to 7 minutes, that's our fuse cool cycle. Think about a jelly donut. So those pipes have been stuck together. It's a jelly donut inside. We don't want to move it. We want to keep the pressure on it until it cools off and it's no longer a jelly donut. It's solidified inside. That data logger gets us to that information so that we know that that pipe can go in the ground, even though we were on vacation last week. Fabricated fittings. So typically molded fittings are up to 12-inch. Integrity Fusion's making some a little bit larger now. Excited to see what their new catalog brings to us here later this year. But fabricated fittings have what's called an equivalent dimension ratio. Stephen, could you explain what an EDR is and why I can't pay attention to just knowing what the DR is?
Yeah, so EDR stands for equivalent diameter ratio. So when you're making a fabricated fitting out of polyethylene pipe, because it's a different geometry, the stress profile is going to be different. So if you start with, let's say, a DR9 polyethylene pipe, and you cut it into segments and refuse it into these different geometries, that DR9 fitting or elbow, for example, can be joined to DR11 pipe because it'll now have the same pressure rating. It started out as DR9, but because the stress profile is different, it now has the pressure rating of a DR11 pipe. So it's one EDR difference. And so that's just a good way to remember that when you're ordering these or specifying these fabricated fittings like this, make sure you tell them what size pipe or what type pipe you're going to join it to and what pressure rating it has to have. And they'll make through the standards process, make sure that it has those properties. So if you see that EDR versus DR, it just means that the pressure ratings have been equalized based on the stress profiles of those products.
Yeah, just point of clarification, EDR stands for equivalent dimension ratio, not diameter ratio.
Oh, sorry about that. Yep.
Yeah. So that image on the left is a fabricated fitting being fused onto the end of a pipe string. So if you can draw it on a napkin, these distributors, they can create it for you and they'll put it in AutoCAD so you can sign off on the AutoCAD drawing before they spend time in the plant. Go ahead, Stephen.
Yeah, I mean, that's a good point. Whatever you can come up with on a drawing, whatever type of installation conditions or trench conditions you have, and you need a special manifold system with different outlets, that can be easily manufactured in the factory, shipped out to the job site, and joined either in the trench or above the trench to make sure you have that fully non-corroding polyethylene system, rather than having to go to some kind of a ductile iron fitting or some other type of metallic fitting that then you'll have to put cathodic protection on later on.
So that image on the right is pretty cool. Those are sweeps. Eric Nichols from Pipestar, he's down here with us this week in Houston at Texas Water. He makes these up in Saskatchewan. Hopefully they can get them across the border. But the image on the left is really pretty cool. So this is the best practice, Stephen, for connecting to legacy materials. It's called the mechanical joint adapter. And Stephen, you're welcome to narrate what you see here.
Go ahead, Peter. You have more experience on this one. I love this video though.
Well, as Dan Landy likes to say, this is our most popular video on YouTube. That's not saying a whole bunch. But we have thousands of views, like 30,000 views. So here we are connecting polyethylene to a PVC main after a pipe burst. And we've got to cut it. We're going to put in a new T, a ductile sleeve T on this PVC line. And at grade right now, we are building the polyethylene spool with 2 mechanical joint adapters on it. And please don't get mad at me for having an unsafe trench. It wasn't my job. I just happened to be filming, but we are under a pavement that hasn't been properly reinforced. So here's that sleeve that we're going to connect to. Now they got the guys at grade. They're putting a mechanical joint adapter. They come as kits or as separate pieces, and they are fully restrained, Stephen, aren't they?
Yeah, so mechanical joint adapter like this is the preferred way, and you can see that is butt fused onto the end of that piece of pipe. There are mechanical MJ adapters or MJ fitting, I guess if you call them, and they do work pretty well up to about 12-inch. But using this fused on MJ adapter gives you a much more robust joint. You can see here it goes into place just the same way in any type of ductile fitting or valve or hydrant that you may have in your system, and provides that fully restrained joint just as you would with any MJ. But again, recommending to use the fused on MJ adapter rather than a fully mechanical if you can. If you have to go mechanical, those are available as well.
So it comes with a backup ring. You see the tech is putting the gasket on right now. These are molded ends, and it has a flange on it, so the backup ring has something to hold on to.
Yeah, just make sure you put your backup ring on first before you fuse it to the pipe.
Awesome. Thank you, Stephen. We're just like PVC. We need tracer wire. You can't find it. Here's a pretty unique way to put tracer wire on your polyethylene pipe string as it goes in the ground. So as the pipe string goes in with pipe bursting, notice how the spool is spinning with it. So it's connected to the pull head. Imagine if I had a product, I got a great product. You got to start using it. It's called polyethylene, but I want you to wrap it in ductile iron first. Well, that's what the ductile folks are asking us to do. They're asking us to coat the inside with cement, put a zinc coating on the outside, and then wrap the whole thing in polyethylene encasement. They came up with a brand name for it called V-Bio because they don't want to call it Hdpe. That's what it is. We're not asking you to coat our pipe in anything. We're just asking you to use our pipe. One of the cool things Stephen and Richard and I have noticed over the years is our mechanical connections keep getting better and better and better. We've got these custom repair clamps and connections that Robar makes. On the right-hand side, we've got George Fisher Piping with their Waga series, the red ones. We've got the Hymax band clamps. When people say to me, how do I fix polyethylene? I say, well, how do you fix it today? You drop in a spool piece or you put a Hymax band clamp on it. Same thing with us. It's just different. The best practice for us would be a spool piece of polyethylene. In the upper left-hand corner there, we have an AVK Series 66 valve that we saw on one of my videos earlier on. Tega makes some great products. We've got this custom manhole. The structure business for us is booming, whether it's underground tanks or it's manholes. Richard, go ahead.
Yeah, I just want to reiterate, on these mechanical fittings, earlier on in our processes of developing these mechanical fittings for polyethylene, we saw in the field that they were some of these flanges and connections that were used for ductile iron were used for polyethylene, but they're everything. There are differences between them. One, radiusing the curves in the contact faces of the flanges where they connect, where the rings lean up against, is very critical. When those were sharp edges, those created some pressure stress risers within the thread, but that's all been eliminated now. For the clamping, just holding that pipe in place, because if there is movement, especially with Poisson's laws of expansion, when you fire up the line, you got to be able to hold that pipe in place. So those are very, very well designed for polyethylene specifically. So the distributors that are operating in our current markets, they understand this and make sure that you ask that question. If you're going to use a mechanical fitting, has it been designed for polyethylene? And then or use the appropriate one.
Thank you, Richard. Yeah, so on the penetrations on that manhole, You kind of want to know those ahead of time. They tend to all be custom. This is a booming business for my member companies for sure. And we're now making full polyethylene or polypropylene ball valves, quarter turn ball valves. That's exciting. All right, moving on to the final section here for us. Tom O'Rourke at Cornell University did some great work over his career. He's now retired. He produced this video on the right where we see humans for scale over here, but we're simulating polyethylene pipe running across a fault line. And the purpose of this study is to say, okay, hey, can you break the polyethylene? Can you damage it? What happens to polyethylene when it's on a simulated fault line? Well, here's what it looks like on the inside. So same movement, same moment, different camera. Here's that pipe moving 4 feet across its 35-foot length. And Richard, was there any damage to this HDPE pipe?
Yeah, this was a great study. I know Dr. Tom O'Rourke wanted to simulate this, but this is a prime example of the viscoelastic behavior of polyethylene. And the answer to your question is no. The reason it's no is because that distance that it was moved didn't exceed the yield point of elasticity of the pipe itself. So when they actually started to unbury that pipe, the pipe wanted to go back straight. So think about that. If you had this kind of situation where it was an extreme earthquake event, and you needed fire, and that was your fire line, well, your fire line stays active because you have not impacted the ability to hold pressure, plus it still remains open. I mean, again, it's extreme, and this is a very controlled event, but it's just a real prime example of that viscoelastic behavior below the yield point.
Thank you, Richard. And then anecdotally, this is actually a fact, I went to the Napa earthquake 3 days after it happened. I interviewed the engineer in the parking lot, and I said, "Hi, how'd it go?" And well, we have a lot of breaks. It took them 6 weeks to fix it all, and they didn't use any polyethylene. So their failures were in cast, ductile, and PVC. What they didn't know at the time is Napa Sand had been using poly for 30 years, had more than 50 miles of polyethylene in their system. They had the same earthquake at the same time. They had 6 failures in AC pipe, no failures in their 50 miles of polyethylene. So here we have, use it, don't use it, your choice. What do you want to end up with? I'm not saying polyethylene is indestructible. Here we have an image where a thin wall polyethylene was kinked by a contractor. So Ian, how do I fix that kink?
Yes, you'd end up cutting out that section depending on if it cracked or had extreme stress whitening, and then you'd move, like I was saying, with the squeeze off 2 diameters away from that point, and then you'd fuse again.
Exactly right. That's how easy it is to fix. When in doubt, cut it out. If you're worried about, can you bend it, like this image on the left, look at your bending radii. It's published in at least 2 different publications that you get from us. But here we have Murphy pipelines bending polyethylene 90 degrees around a neighborhood. So here we have a guy who fused up the polyethylene pipe in a schoolyard and then dragged it across this dirty road. And look at what he did to his polyethylene pipe. The inspector was angry. He's like, I paid for new pipe. This is not new pipe. But remember, Steven said that 10% gouge or scrape rule? This did not exceed that. This one, how do you know? Because you don't know how thick the pipe is. But this was on a 3-inch wall thickness of polyethylene. So that was not a 10% gouge. So that was fine as well. So we know this about polyethylene. We know that it's a softer material, but it's an extremely tough material. And that 10% rule has been studied in great detail. We're just like PVC in that our C factor is 150 for the life of the pipe. We do encourage you to learn how to read a print line. Stephen, why is a print line important?
Yeah, Peter, that's actually one of the more important parts of a pipe. And the reason for that is several things. First of all, it tells you what size the pipe is. So you got the OD, the nominal OD, whether it's IPS or DIPS. So it's very critical. And the DR of the system. You can learn a lot from that. Tells you who the manufacturer is, the type of material that is used, but also the standard the pipe's made to. So whenever a pipe manufacturer prints the standard number on a piece of pipe, that means they're asserting that that pipe has been manufactured and tested in full conformance of that standard. If it's AWWA C906, it's been tested to that. ASTM F714, it's been tested for full conformance to that. So that's your conformance certification right there. It'll also tell you whether the product's NSF certified for potable water applications. It can be NSF 61 or NSF 14. Those are both potable water certification marks that can be used in drinking water standards and potable water contact. The standard 14 also brings an additional performance certification with it as well. So there's a lot of information there. It should also be recorded to make sure you're getting the right products on the job site that you think you're getting or supposed to be getting.
Thank you, Stephen. If you want to go deep on the accountability triad, go to our YouTube page and you can watch a 75-minute webinar on that. You can get polyethylene in all kinds of stripes. We've got this UV protection that keeps us safe from the harmful rays, unlike PVC pipe. We do have gray pipe that has a 36-month outdoor life before we start seeing degradation. But the black pipe is for the 100 years. Ian talked about the sinkhole. Yeah, you know, we're just so used to sinkholes. You don't see those kind of failures with polyethylene. I want to thank the Discovery Channel for this. This is kind of like what not to do.
A lot harder than it needs to, so it's smarter to just have it in a straight line. It's where we had it, but we've been slowly moving it around to make way for our tailings, and now it's just kind of gotten to look like a snake. So I just need to straighten out a few of these bends and improve efficiency with that pump and not make us have to work so hard. I mean, it's the only one we got. We need it to run for the rest of the year. Damn it!
All right, so the lesson there is, you know, don't fight rocks and the bucket teeth. We're going to lose that battle.
A lot harder.
So here's Dante. We got this from TikTok. So here he is tapping PVC, and you'll notice the failure shows up here to the left.
Dante Kent down here in the hole. Oh, that's cool.
You're not going to see these kind of
There's Dante.
polyethylene errors in
Yeah, you don't want it to
polyethylene
pop
when you
off
tap
right
it
there,
with
right?
a
That's it.
dull hole saw.
Almost like it's hole.
So you see that crack. So that hole saw caused a failure in the PVC and it ran to the left there. And this image I love to talk about because here we have a clamp here and a clamp here, and these guys are trying to fix it. And you notice how the crack runs. You're not going to get, this is not how polyethylene fails. You don't fail in this manner. You can still use the same band clamps, but you're not going to get a running crack. This also will recognize as an unsafe trench. Where's the ladder? Where's the scuba gear?
I don't think scuba gear is proper PPE in this case, but probably necessary.
So
Yeah.
if we didn't have unsafe trenches, we wouldn't have lots of videos, unfortunately, but that's just the way that is. Good job, Pete. Way to
Yeah,
capture.
well, thanks, everybody. Stephen, Ian, come on. Richard, I want to say thank you to our audience.
Thank you, everybody, for sticking with us for this long. You've done really well to give us the time investment that you have for the Alliance for PE Pipe. Hopefully we were entertaining for you. Stephen, Richard, any closing arguments?
Yeah, I just want to thank everybody for the great questions. And again, utilize these resources. We're here for you. We've me and Stephen together, I think I don't want to even say how many years experience we have, but we've known each other a long time, and we've went from the resin manufacturing all the way to, you know, to your end, to the installation, manufacturing, and everything. So please utilize the resources. We can help you, and we can help you point you in the right direction.
Yeah, I absolutely agree. Thanks for everybody for spending this afternoon with us. I hope you learned something or at least generated some additional questions that you may have. Feel free to contact any of us anytime. Again, I know this is just the start, and we have a lot more in-depth information as you get into your design for your systems.
Yeah. Thank you, Alan Ambler, for putting it together. And thank you to the audience. Stay tuned. You're going to get your PDH and your CU by responding to the questions. Thank you all.
Thanks, everybody.